So welcome everybody. This is the seventh session of the Octoscope tutorial series. This time we're going to talk about antennas. What are they? What do they do? What are some of the details such as gain, polarization, near field, far field, etc. We're really glad that you guys could join us this morning, or whatever the time is in your part of the world. Let me introduce the speakers. This is Jan Nelinkola. I run marketing for Octoscope. I recently joined a couple of weeks ago. The main speaker will be Lee Chinitz. He is an old veteran of the industry, has worked in Wi-Fi, cellular, has worked in at FCC, has worked in, participated in the work of various standards bodies, Wi-Fi Alliance, IEEE, ITU. Lee has 20 patents on his name and has a PhD in physics, among other degrees. Before we get into the tutorial itself, I just want to remind everybody that you're free to ask questions during the discussion at any time. Just use the tools to raise your hand and we'll take your questions. So with that, Lee, the stage is yours.
All right, thanks, Jana. As an old veteran, I would just like to say I'm no longer speaking to Jana. That's okay. So as described, we're going to talk today about antennas, and also as mentioned, this is our seventh tutorial. So I guess we'll keep doing this as long as people keep showing up. So thank you very much for showing up. Again, the topic today seems like a pretty basic one. Antennas, very similar to other kind of more basic ones we've done, like link budgeting and things like that. But why antennas, right? Antennas are a very key component if you're talking about a test bed where you're focused on doing over-the-air testing, as we are. So antennas are a key element. It's important to understand. We get a lot of questions about them. We thought it would be worth going through some sort of key topics. Okay, so that being said, let's start by getting one thing out of the way. This is for the English-speaking, I guess, members of the audience. These are antennas. These are antennae. I can't tell you how often when I'm having a conversation, people will say something like, wait, is it antennas or antennae? How should I be saying that? When we talk about the kinds of antennas that we're using for communication, we call them antennas. If you have antennae in your test bed, that's probably a bug. Pause for hysterical laughter for the bug joke. Okay. All right. How do antennas work? So we're going to start with some pretty, basic stuff here. How do antennas work? Answer to that question is that. So thanks for attending. See you next time. That was the shortest in our tutorial series ever so far. Just kidding. Those are in fact Maxwell's equations that describe electromagnetics, and they are in fact equations that could explain in great detail how antennas work and what the fields nearby them look like. But I don't actually know anybody who is an antenna expert who knows everything that they know about antennas just from understanding Maxwell's equations. So let's dig in a little bit, right? So seriously, what do we know? We do know a couple things from basic physics. It's always good to start with a little bit of basic physics. And we know from basic physics that if you have an electric field that's changing, that creates a magnetic field. If you have a changing magnetic field, that creates an electric field. If you take a wire and you run current through the wire, you'll get a magnetic field around that wire. It'll be static, but that's what an electromagnet's all about. if you start changing that current, so use alternating current, for example, so that the current goes up and down the wire, you'll get a changing magnetic field. That magnetic field will flip back and forth, and that results then in a changing electric field, which results in a changing magnetic field, and so on and so on. So if you look at this picture, this gives you a kind of a simple but useful, I think, understanding of how an alternating current in a wire generates these fields near the wire. So we have these blue circles that represent the magnetic field. You can see they're sort of horizontal in this picture. And these red circles that represent the electric fields, and they are vertical in this picture, and they radiate away from the wire itself. And that's why when people talk about light, and I put light in quotes here, and you'll often see a picture like this. You'll see that the light is moving, and there are two pieces to it. There's an electric field, and then there's a magnetic field, and they're at right angles to each other. I put light in quotes because I'm pretty sure that everybody here knows that electromagnetic waves are all pretty much the same. The only difference between light and anything else is that it's at a different frequency, and one that our eyes are sensitive to, but it's the same story for light waves or radio waves that we use for communication. The only difference really being the wavelength shown here as lambda. That's usually the way people talk about wavelengths. So the distance between the peaks of these fields. All right, so now, that being said, we have our basic physics out of the way. So what's an antenna? So an antenna, basically a piece of wire that's connected to a source of alternating current. And as described, we can then drive the current up and down this wire, and that will cause electromagnetic waves to radiate. It actually works in reverse too. Almost everything that we'll talk about today works in reverse. So if you actually hit a wire with an electromagnetic field with electromagnetic waves, that will actually cause the alternating current to go up and down, and that's what it looks like when an antenna is used as a receiver. So an antenna can both be a transmitter, where you cause the waves to come out, and it can be a receiver where when it receives those waves, it creates a current. Oh, this is too bad. Oh, there we go. Okay. So, so the energy then that comes out of antenna looks something like this. So in the picture on the right, we've got our little wire, and you can see that we've got current being driven up and down, up and down. It's flipping back and forth, positive to negative, negative to positive. And the frequency at which that flipping back and forth is happening is, in fact, the frequency of the waves themselves. Because light travels at the speed of light, hence the name, there's a relationship then between that frequency and the wavelength, which is shown here. The speed of light is equal to the frequency times the wavelength. And if the length of our antenna is about half of the wavelength, then we would get the energy shown in this picture. So the energy that's coming out of that antenna shown in this picture is basically what would be happening in a slice. If you think of this slide as being a slice in space, that's what the field looks like as it comes out of that antenna. In 3 dimensions, it looks something like this. And you can see those slices, for example, are these red circles or green circles. You can slice either way. It's symmetric all the way around. It looks like a donut, and it's referred to as a toroid. And that's what the energy, the field coming out of what's known as a half-wave dipole looks like. So now, I've said a half-wave dipole a couple times. I said that if the the length of our antenna is half of the wavelength, it would have that sort of pattern. So why do I keep focusing on half of a wavelength? Another really useful way of thinking about antennas is to think of them as similar to strings. And the reason is that people are much more familiar with strings than they are with electromagnetics. A lot of people played with strings, and you can see this guy here playing with this nice long string, and he's got one end of it attached on the right-hand side. The other end of it, he's holding in his hand, and he has basically kept that fixed. And he is now vibrating that up and down, and he's looking for the resonant frequencies, the frequencies at which he can make that string vibrate. And this is something that a lot of people have done, just playing around. And what if you've tried to do this, is that you can only set up those waves, those resonant frequencies for specific frequencies, so or specific wavelengths. Essentially, what you need is for the string to be able to remain fixed at the points at which it's fixed. So the very longest wavelength you can get is one where you've got a fixed point here and a fixed point here, and so the string is again then becomes half of the wavelength of the frequency. And you can do that for any multiple of half wavelengths. You can do 2 half wavelengths, 3. This guy's got 3 going here. You can kind of see 3. He's got fixed over here, and then he's got one peak, another peak showing up down here, and a third peak over here. And then 4, et cetera, you can keep going. So again, the frequencies that you'll get are multiples of half a wavelength. And it's pretty much the same with antennas. The half wave dipole that I talked about before, again, has this shape that I described, this toroid, this donut shape. And it is basically, if you want to think about it, kind of fixed at the top, fixed at the bottom, and then it's got this this peak out here towards the sides. And so it's got a node at each end and a wave between the two. You can use different length antennas if you want. For example, you could have an antenna where it's a 1.5 wave dipole, and that would again have that shape, kind of like that guy was getting in that little video clip before, where we have essentially 4 nodes, the 2 at the fixed ends and then 2 in the middle. And if you look at what the antenna pattern looks like in that case, it looks like what's shown here. And again, it's not surprising. Essentially, you have you're fixed at the top and the bottom. You don't have energy coming out directly up or directly down. You've got a big lobe here on the top. You got a big lobe here on the bottom, and you have 2 nodes in the middle and a third lobe directly in the middle. So the pattern basically reflects this kind of shape. So for communications, basic communications, half-wave dipoles tend to be the rule. If you think about it, and let's think about kind of a specific application we're talking about, like an AP, a Wi-Fi AP in a home, which is trying to provide coverage, pretty much everywhere in the home. You tend to want the energy to go in all of the directions. Same is true for a cell phone, for example, where the person holding a cell phone doesn't know where the base station is that they're talking to, and therefore the right way to design that is so that the energy coming out of that cell phone is going in all directions, so that it can communicate with the base station anywhere, or no matter how that person is oriented. And that's called omnidirectional. So the energy is coming out in all directions. We typically don't usually want the kind of nulls seen in that 1.5 wavelength dipole plot where we had those 2 big nulls in the middle. That would mean there would be very poor communication if the access point, for example, or base station happened to be in the direction of one of those nulls. We usually don't want that, and that's why the half wavelength dipole is a really common communications antenna. And the whole purpose of this discussion is to then point out that the size of antennas then are directly proportional to the frequency at which they're operating. As I said before, the frequency is related to the wavelength. We've just talked about why it's kind of important to use antennas like half-wave dipoles, meaning that whatever frequency you're operating at is directly related to the size of the antennas. So, for example, if if anyone's ever seen pictures like this, like from the 1940s, of various communication devices, like military radios here on the right, you always see these guys walking around with radios and then these just crazy long antennas. The reason for that is that back in the day, people were operating at about 50 megahertz. The wavelength at 50 megahertz is 6 meters, about 20 feet. So half wavelength dipole would be 10 feet long. So, you now have some idea why, back then antennas were always shown as being these really, really long things. But as technology has gone to higher and higher frequencies, antennas are getting smaller. And that's, obvious from all the discussion that we've had. But just to give you a sense, 50 megahertz, if you look at the wavelength at 50 megahertz, like I said, it's about 6 meters, roughly the size of a giraffe. As soon as you move to 800 megahertz, the kind of the low band cellular frequencies around the world, 800, 900, there you're talking about 37-ish centimeters, about the size of a bowling pin. These two pictures are roughly to scale. So you can see the dramatic difference as you move up in frequency. And then the rest of these pictures are not to scale because you wouldn't be able to see them if I did them to scale. Once we move to the 2.4 gigahertz band, we're talking about 12 centimeters, so a few golf tees. 5 gigahertz, the upper, up until recently, actually, the upper Wi-Fi band. Wi-Fi is now moving to 6 gigahertz, but up until recently, the highest Wi-Fi band, 5 gigahertz, just a set of aspirin. And then if you look at millimeter wave bands, then we're talking very small sizes. Something like if we're talking about 25 gigahertz, we're talking about maybe a centimeter or so, which, by the way, is the reason that in the millimeter wave bands, it's possible to start building antenna arrays even into small devices because the antennas themselves are so small. I think I saw a question. Is there a question we need to take?
Yeah, there is, from Harold. It says that a quarter wave antenna are also commonly used.
Yeah.
What are their characteristics? If an antenna is not exactly halfway, say it's 40%, does the efficiency drop? For example, if the power gets reflected back down the wire instead of radiated?
Yeah, that's exactly right. I'm going to actually talk a little bit about that in just a second. But yeah, you're right. Quarter wave antennas are used. There's trade-off between kind of optimal efficiency and size. You need to be able to put the antennas in the devices that you're building or on them. And you can imagine how that woman in that picture before, with that huge long antenna. I mean, that may have been acceptable back in the 40s, but aesthetically, it's not acceptable anymore. When I remember seeing early cell phones, there were still those whip antennas that people had to pull out. Of course, we don't see that anymore. Nobody would put up with that these days, and so there's definitely a trade-off there, and you're essentially trading off antenna efficiency for aesthetics. So let's talk about that a little bit. So antennas then not every antenna is going to work at every frequency. You can try just like you can take a string and you can try to oscillate it at whatever frequency you want, but it's not going to work as well as at one of its resonant frequencies. So since the antennas are related to the frequency of operation, you kind of need different antennas for different measurements. Just as said in the question, when an antenna is used at a frequency outside of its design range, then what happens is, if you think about our little picture before about the current being driven up and down the antenna, and that resulting in energy radiating away from the antenna, what happens is that not all that energy does radiate away. In fact, exactly as asked, it bounces back into the transmitter. And so essentially the antenna becomes less efficient when that happens. A measure of that is what's known as return loss. So when people talk about return loss, that's exactly what they're talking about. They're talking about how much of the energy bounces back. So a return loss of negative 10 dB means that 10% of the energy that you're putting into the antenna bounces back in. The other 90% gets radiated. That's pretty good. There's no, as far as I know, there's no single value that people require for return loss, but something like 10 dB or 15 dB is a reasonable place to look at when you're talking about what where an antenna is operating optimally. So return loss plots tend to look like this. On the vertical axis we have return loss, and on the horizontal axis we have frequency. And what you can see here is that there is a point at which the return loss is very, very low, meaning all the energy is getting radiated. So this antenna is clearly designed to operate around 2.45 gigahertz. But it does operate at frequencies on either side of that. And you can ask yourself, so kind of where should I use it? And if you use 10 dB, negative 10 dB return loss as the answer to that question, these markers show that that's between about 2315 and 2580, so about over 260 megahertz or so of bandwidth. So this antenna is designed to work at about 2450, plus or minus, with a bandwidth, sorry, not plus or minus, with a bandwidth of about 260 megahertz. But not all antennas have a bandwidth that looks like that. Depending on your design, and you can put more focus into your design. If wide bandwidth is what you're looking for, you can actually get antennas that are quite wideband. Anybody who has had the opportunity to use an octoscope testbed will recognize the antenna that I'm showing here on the lower left. This is we refer to as our high gain antenna. And if you look at the picture on the right, you can see the return loss plot, same picture as before. Return loss is a function of frequency. And if we draw a line at negative 10 dB, you can see that the return loss, negative 10 dB return loss bandwidth for that antenna is over 5 gigahertz, not operating at 5 gigahertz, but 5 gigahertz of bandwidth from about 2 gigahertz up to over 7 gigahertz. You can also see, by the way, something very important, that when antennas are designed that way for specific ranges, the return loss can change quite quickly. You'll notice that below 2 gigahertz, the return loss rises quickly, and so it is important to know what the operating range design of the antenna is. I see some questions we should take.
No, I think it was just a comment.
Okay,
Yep.
Good. All right. So I mentioned that this is Octoscope's high gain antenna. So let's get into that. Why did I bring up gain all of a sudden? We mentioned it. Let's talk about it. We actually mentioned gain in a previous tutorial that we did where we talked about link budgets, and so it's worth getting into a little bit here. Without doing more math, I like to use more kind of easy ways to understand what's going on, sort of think about models for this. And this is a well-known model. It's not one I made up, but it's, I think, a very convenient way to think about gain. If you think about the dipole antenna that we talked about before, right, where we have that sort of donut shape, and we have basically no energy being sent up or down, but kind of all out in this big donut kind of shape. As that antenna gets smaller and smaller, that donut gets fatter and fatter. And if you go all the way down to sort of a point antenna, you can imagine the energy being radiated out into just a big sphere in all directions. It's not a real thing, but it is the sort of mathematically perfect antenna that people in the business like to use as the default model. It's known as an isotropic antenna, and you can think of it as energy being radiating out in a perfect sphere, kind of like a balloon. So the energy would come out, it would look like this balloon. Now, if you design the antenna in such a way, you can what you can think about is that you can take the energy that's in that balloon, but you can squeeze it into different shapes. So the dipole is one example of that. The dipole, as we said, it didn't have energy going up or down, but it had it going out in that kind of donut-y shape. But other designs are possible too. For example, directional antennas. In a directional antenna, you can imagine sort of squeezing the balloon so that all of the energy is going out, in this example, to the right of this picture. So if you were on the right-hand side of this slide, you would have quite good reception from this antenna. But if you're on the left-hand side of this slide, you would have quite poor reception because very little energy is going out in that direction. Again, so think about the balloon as having a volume, which is the energy that it's putting out. And when we squeeze it, we don't change the overall volume. We just change where it's going. And antenna designs, are really sort of all about that. Now, why would we want gain?
Oh, I'm sorry. We do have a question.
Oh, yeah, sure.
Natasha's asking, how do we optimize return loss for any antenna?
Well, I mean, return loss is a characteristic of the antenna, right? I mean, you can't optimize it. What you can do is choose the right antenna for the test that you're doing. So, for example, part of the reason we have such a wide bandwidth antenna in our test bed is that we want people to be able to do tests throughout the frequency range that the test bed supports. So we typically say that our test bed supports from about 2 gigahertz up through about 7.5, 8 gigahertz. And if you looked at that return loss plot for that antenna, you would see that. But we also have so for example, if you wanted to use the test bed, but for example at a lower frequency, we do get requests from that from time to time. Let's say 900 megahertz. You can see that the antenna that I showed, would have quite a high return loss at 900 megahertz, but it's certainly possible to get 900 megahertz antennas and use them. So that is what you do. So return loss is really an antenna characteristic, and you use that in order to design your test. So, why would we want gain though, or directionality? I said something before like, hey, half-wave dipoles rule, because, you don't know where anything is and you want to radiate in all directions. But that's not always true, right? If you look at an example like the one shown here, where I've got buildings, let's say, and one building is sending a signal to another building back and forth. Those buildings aren't moving, they're moving with respect to each other, and therefore radiating energy out in all directions doesn't actually make a lot of sense, because I only want the energy to go to this building on the right, and for the right I want the energy to go to the building on the left. So I'm doing a lot better if I can actually squeeze the energy into a narrow beam and point it where it needs to go. The advantage there is that that contributes directly to the link budget. I'm not going to go into details on link budgets. We did that in a previous tutorial, so anybody who's interested, please take a look at that one. It's called Fundamentals of RF Link Budgeting in Wireless Testbeds. But the basic point is that the more energy you can point in the direction of the receiver, the better that receiver is going to be able to hear you, so you can go further. So if the transmitter and receiver are in a stable orientation relative to each other, then a high gain or directional antenna may be just what's called for. So how does that relate to test beds then? In a test bed, we will have a device under test, like the one shown here. In this, I know it's just an image, but it's representative, and you see this quite a bit. You'll have, for example, an access point or small base station, something like that, and they will have dipole like antennas with dipole characteristics. They'll be transmitting sort of omnidirectionally everywhere, and there will be test antennas that are interacting with this. Now, those test antennas tend to be placed near the edge of the RF chamber itself, right next to the RF absorber, which is what's being used to create the anechoic environment in the test bed. So if we put a dipole antenna as our test antenna, then we will have this pattern. And again, if you can think of this right now from the point of view of this being a transmitter, as I said before, the whole thing is symmetric. It's true in terms of receiver, but maybe easier to think of as a transmitter for right now. So this thing is transmitting energy. Energy is coming out in all directions. It's omnidirectional. And basically half of that energy is going directly into an RF absorber. The whole point of the RF absorber is that it absorbs the energy. It doesn't go anywhere after that. It's not like it's getting reflected back out, right? The whole point is that it's not. And so essentially the energy is being transmitted, going into an absorber and disappearing. So that's kind of a waste. So there's actually a role for directional antennas even in wireless test beds. Because if you use an antenna like the one I showed before, where we were talking about the return loss, and it has a shape something like this, you can see most of the energy is now heading in the direction of our device under test, and very little of it is being directed back towards the RF absorber. So in addition to wide bandwidth, I just kind of mentioned that in the previous slide, the antennas, those high gain antennas actually do have directionality, they have gain. These are the actual antenna patterns shown for these antennas, and they're just being shown sort of in different slices of three-dimensional space. But in basically all of the slices, they look pretty much the same. You can see the energy is being preferentially sent out towards the tip of the antenna. And
I'm sorry, it looks like we have a follow-up. It looks like
sure.
Nitish is again asking, in that case, what purpose of providing matching network at IP of antenna? So I think, is it a follow-up to his previous?
Yeah. In that case, what is the purpose?
Well, matching networks are very common. I mean, you always have one to the antenna. It's part of the circuit design, I guess. So they are the ones that optimize return loss. Did I answer the question? I'm not sure. I'm not sure I completely understand. But they're always there at the antenna. They match the antenna to a 50 ohm, usually 50 ohm connection. And the chip, whatever the chip is driving the antenna, it would be driving it through 50 ohms.
hopefully that answers. Otherwise, we can always, by the way, please feel free to reach out to us after if we're not able to address whatever question you have during the tutorial, and we're always happy to keep the conversation going. So there's one last topic related to antennas, and that's the issue of polarization. If you remember that first picture that we showed with the alternating current and the radiating fields, and I mentioned that it works in reverse too. If you hit an antenna or a wire with a field, you will generate a received signal. So that's what I'm showing here. If you take a wire oriented in the same direction as the transmitting wire, when this electric field reaches it, it will drive a current, and that's our receiver. So polarization, when people talk about polarization, it actually refers to the orientation of this electric field, these red circles here. But if the transmit and receive antennas are not similarly oriented, as in this picture, like imagine putting one at right angles to this, then you can kind of just imagine, just by looking at it, that these electric fields are not going to be very efficient at being able to drive a current, meaning this antenna will not necessarily be a very good receiver for this transmitter. So are those antennas that I mentioned before? Now we've talked about the return loss of those. We've talked a little bit about the gain of those. How about the polarization? Are they polarized? The answer is yes. These antennas are what's known as log periodic antennas. They're built from what are essentially a set of little dipoles. If you look at these small traces on this design, you can think of each of those as a little dipole. We talked before about how lower frequencies have longer wavelengths and therefore need longer antennas. So you can kind of see how what we're looking at here are a set of antennas designed to handle different frequencies, from lower frequencies up to higher frequencies. The log, by the way, in log periodic has to do with the spacing between those antennas, which are in a logarithmic pattern. So the polarization then is basically the same as the polarization of dipole antennas, just along the dipoles shown here. Okay, so that now is kind of the basics of antennas, things like gain and return loss and polarization. I want to touch on a topic that is very common, which is this topic was known as near field versus far field. We will often talk with customers about what people refer to as near field effects or things like that, whether or not a small chamber is able to perform very well because of near field effects. So what is the near field, by the way? Let's just define it for a second. Those equations that I showed you before, Maxwell's equations, they are correct everywhere and they can be solved everywhere in space, but they're a lot easier to understand when you're far away from the radiator. When you're far away, you get those patterns that I showed before, where you have electric field and magnetic fields that are at right angles to each other, and what people tend to draw when they're talking about light or radio. Nearby the transmitter, the relationship between the electric and magnetic fields is a little more complicated. You have terms in those equations that are really only valid nearby. And then the electric fields and magnetic fields aren't necessarily only at right angles to each other. They have a much more complicated shape. And that's what people refer to as the near field. Where is that? Terms like near and far don't help that much. But the near field actually depends on the frequency that you're operating at and the size of the antenna. I've put antenna in quotes here. I'll explain to you why in a second. 3GPP actually defines the radius where the near field ends and this is their definition. It's related to, as I said, the frequency or the wavelength. And then D here is what I have as antenna in quotes. It's actually the biggest dimension of whatever is doing the radiating. So, for example, in a laptop, even though you might have an antenna built into the laptop, the entire laptop case will participate in radiating, and therefore the equation here talks about the largest dimension, not just the antenna itself. So if the thing doing the radiating is, let's say, 25 centimeters, not an unreasonable, size, and the frequency is, let's say, 5 gigahertz, obviously some like a Wi-Fi kind of frequency. The wavelength at 5 gigahertz is 6 centimeters long. So if you throw that into here, you see that the near field extends out about 200 centimeters, so 6 feet. Which means that for typical measurements done in an octabox, those measurements are in fact being done in the near field. I mean, people ask us about that, and it is true. In many cases, measurements in the octabox are being done in the near field. So let's address what I like to call the elephant in the room here, which is, can we do MIMO-based performance testing using antennas in a near field, in a chamber in which we're in the near field? Short answer to that question is yes. And if that's not good enough, then I will have to go into some detail. If you're not going to trust me, which I can sense through Zoom that you're not, then I will give you a little more detail. If you want a lot of detail and this picture doesn't scare you, then I would encourage you to take a look at the PhD thesis that is available on our website called Near Field MIMO Channel Modeling with Applications to Small Anechoic Chambers. This was a PhD thesis in which some very detailed measurements and a lot of detailed analysis was done specifically of the octoscope testbed and the antennas that I've been describing. But if you don't necessarily want to dive into a full thesis, let me summarize some of the important points. So one of the key takeaways from it, right, is what they mention is that large over-the-air test chambers, big anechoic chambers, can be quite expensive, but research is showing that you can actually do MIMO OTA testing in a much smaller anechoic chamber with a set of probe antennas for significantly reduced cost and still be able to get quite good MIMO over-the-air performance. As I mentioned, the paper itself looked specifically at an octoscope testbed with octoscope log periodic antennas. And let me just give you a quick insight into what they took away. What I'm showing here on the right-hand side, this square, think of this square as being the outside of the octoscope testbed. And imagine we're looking down from the top. So this colored square, this little grid in the middle here, is taking a look at the center of the testbed where the device under test would be. So you can see I've circled here, it says device under test central coordinates. So this is the location of the DUT in the middle of the chamber. And based on the many detailed measurements that were taken, as well as the fairly complex path loss modeling that was done, they were able to determine what they call the wideband capacity of the testbed, measured in bits per second per hertz. And if you look at this scale here, you can see that the MIMO capacity that they talk about is about 11 bits per second per hertz. So wait, before we get too carried away with that number, it's important to know that those measurements are done at a fixed signal-to-noise ratio. The paper, just for the point, because they just needed to pick a value, used 20 dB of signal-to-noise ratio. That's actually an extremely low value for signal-to-noise ratio. Let me explain quickly why. Remember, we're in a shielded chamber. So in a shielded chamber, the noise level that we have to worry about is only the thermal noise in the receiver. If we take 160 megahertz bandwidth, then the thermal noise at 160 megahertz is about negative 95 dBm. If we assume that the signal level that we can get is something, quite high, like let's say around the top level that is called for by the IEEE 802.11 spec of, let's say, negative 30 dBm, and by the way, you'll see that we can reach those numbers. That means that our signal noise ratio is more like 65 dB. And the analysis then for 65 dB shows that the capacity is more like 75 bits per second per hertz. So is that good? 75 bits per second per hertz? Well, let's see what MIMO capacity we would need to handle 11AX at its most aggressive. 160 megahertz, 8-stream MCS11, 802.11ax is 9.6 gigabits per second, so 9608 megabits per second. And 160 megahertz is 60 bits per second per hertz. So yes, 75 bits per second per hertz of capacity in the test bed is very good. It handles 11AX even at its most aggressive. So having done all that, hopefully convinced you that that these test bed antennas are certainly critical, and also that the test beds themselves are more than capable of handling MIMO testing. Let's do some demos before we run out of time. What I'm going to do is do a couple of demos that are related to all the things I just talked about. The test bed that we're using is a test bed we call the Stack Max. It's the test bed we've been using in all the other tutorials, and I'm not going to get into a huge amount of detail. It has a number of chambers. They're all connected to each other in various ways. Actually, what I'd like to point out here in this picture this time are the antennas. So take a look in this top chamber here. You can see antennas that are all around the DUT, for example. You can see in the lower chambers, we've got cases where we've got multiple rows of antennas on one side, for example. Others where we have only a single row of antennas. So antenna placement in the testbed is extremely flexible and also very important. It's really important to understand kind of what's going on. The other thing I'd just like to kind of highlight here, this is a logical then picture of that same stack, the one that I just showed you. So for example, this one labeled Smart Box at the top, the big one with the access point on a turntable, is the one that had the antennas located all around. One thing, just to so you understand what's going on, is that when we draw the antennas, when we draw these dark blue antennas, we're actually talking about a set of 4 antennas. When we draw these green antennas, we're talking about a set of 2. So here you can see it looks like only a few antennas, but if you look up here, you'll see many, many antennas in there. I'm going to explain why we have so many antennas and kind of why groups of 4 also. So let's do the first demo where we just talk about the ability of a testbed like ours to get very high MIMO counts. So I'm going to run traffic between an access point and a test endpoint, and show you what that looks like. Let me jump over to. So this is one of our test beds, one thing I just want to point out is that I've attached this test bed by browsing directly into it using the browser. This test bed is just on our local network, and this is one of the things that makes using our test beds convenient. You can actually reach them pretty much from anywhere, or actually from anywhere. In this particular case, I've browsed into to an IP address that's on our corporate network. It's actually also possible to go directly over the internet. We have some test beds that can be reached that way as well. Just quick, for people who haven't seen it before, this is our user interface. Our user interface, by the way, is undergoing some major changes. We'll have all this functionality that I'm going to show now, but hopefully in even a more user-friendly and convenient interface. In upcoming tutorials, I suspect we'll start to switch over to that newer interface. But for today, show you this one. We have the ability in the interface to configure the test completely. I have set up traffic here between essentially between the device under test and the PAL, which is the test endpoint. Sorry, really quickly, it looks like that has disassociated. I'm not sure why. So we can get it to come back. I will check in a minute. We can do many other things. We can control our attenuators. We control our turntables, things like that. There we go. Okay. So let me just run some traffic now and show you a couple other things. So now I'm running traffic between my my device under test and my test antenna, my test device. And the point we wanted to make here, right, is that we can do we can handle multiple MIMO spatial streams in the test bed. You can see that over here. You can see that we've got interesting. You can see that we've got 4 streams. Don't know why the test stopped. It was actually configured for much longer than this. So you can see we've got 4 spatial streams. You can see that we're getting MCS 11, the 2400 megabit per second physical layer, and nearly 1.5 gigabits per second of throughput. The signal levels, as I mentioned before, are quite high, which is what justifies our ability to support such high wideband capacity. You can see, so negative 40 dBm, meaning, we have 60, 70 dB of signal noise ratio. Okay. Pop back over now to our presentation. Okay, so one of the things that I wanted to describe here is why we have...
Lee, there is a question we may want to take from Nihar.
Sure.
By the way, Nihar sent us a note. He's using our high-gain antennas. That's terrific. They're actually quite popular in the industry now. So Nihar is asking, can we test the receive sensitivity with the setup for NEP?
Yeah, actually you can. Receive sensitivity is actually one of the tests defined by the Broadband Forum TR398. We talked about that in the last tutorial, so if you'd like to take a look at that, feel free. But yes, you can certainly do that. We have a number of different ways that we test perceived sensitivity, but the Broadband Forum test is one of them. And that one is something that we have implemented in automation and is available to anybody who wants. So one of the things I want to talk about is kind of why we have these groups of 4 all the time. So we're just talking about 4 streams, and we were, I mentioned that we always have, we often have these groups of 4 paths of antennas. I'd like to talk a little bit about the relationship between those two. Imagine we have a 4-stream capable device under test and a 4-stream capable receiver on the other end. And we want to see 4 streams, 4 spatial streams. Well, so it turns out that what's important there is that there be at least 4 independent RF paths between the two. It's kind of mathematically, you kind of get into the details on this one, but it's another one of those things that's actually fairly straightforward to understand if you think about it. In order to have 4 independent spatial streams, the transmitter and receiver have to be able to differentiate between those streams somehow. And that, you can imagine, is not possible to do if you don't have independent RF paths. So as I'm going to show you, if you actually do have 4 independent paths, you can get 4 streams. If you start to choke them down, so if you turn off one of the paths, for example, by increasing the attenuation and leave yourself with only 3 paths, you'll see the system drop to 3 streams. The AP and the station simply will not be able to support more streams than paths. It'll drop to 2 if we leave only 2 paths, and it'll drop to 1 if we leave only 1 path. So let me show you that. It's kind of interesting, and not everyone has seen this before. If you see here, we're starting with 4 paths, and now we're going to do exactly what I did in that slide. We're going to turn off one of them, and if you look, you can see the system immediately drop to 3. Again, I haven't changed the AP or the station in any way. I'm just changing the number of available RF paths. And every time I drop a path, I drop a stream. You see me coming down to 1 here. Now, so as I said, you need the number of paths at least to match the number of streams that you want. And I say at least because you can always have more paths. So let's do the same test where I have only a 2-stream capable device. So if I have a 2-stream capable device and I turn off one of the paths, leaving myself with only 3 paths, I will still get 2 streams. And if I turn off another one, I'll still have 2 streams. But if I turn off that last one, I'm only going to have 1 stream. And I can show you that as well. So again, if you look here now, you can see up there, we've got 2 streams to start off with because we've got only a 2-stream capable device. And if I turn off one of my RF paths, see, I still got 2 streams, even though I've turned off an RF path. If I turn off another RF path, still got 2 streams. I've got 2 paths, I can still get 2 streams. But if I take away that last path and I leave myself with only 1, you can see that the station and the AP are really only able to distinguish 1 spatial stream at that point. And we drop to 1. Other things that are important about antennas, right, is the ability to do things like beamforming. So beamforming is especially important in Wi-Fi for looking at multi-user MIMO performance. And you know, again, one of the questions that we often hear is, yeah, is it possible though to do beamforming in a small footprint testbed like you have there? And the answer to that question is yes. I'm going to show you how that works as well. In this particular case, we are using this box on the right. It's called the PAL box, which has both our Wi-Fi 6 PAL in it, but also a set of 16 other independent station PALs, known as stay PALs, with a variety of operating systems. And we're going to do multi-user MIMO to 2 of them. The way we do this is those 16 stay PALs are actually coming in on these sets of antennas that are located in the corners that I just circled here. You see I've got a set of 2 antennas in all the corners, meaning that the AP is actually able to create beams.
Yeah. Before, sorry for interrupting the flow, but we have a question from Nihar. He's asking, to test 8x8 spatial streams, we need 2 attenuators. Is this correct?
That is correct.
And the current octoscope attenuator we have is 60 dB supported. To achieve 90 dB attenuation, is it possible that current one can be upgraded with software?
Not with software, but it can be upgraded. Our attenuators, our current generation of attenuators actually support 90 dB of attenuation. So it's probably a good conversation, you know, offline to talk about, you know, how to make sure that you've got the functionality that you need.
All right,
so I'm going to quickly go through the this multi-user MIMO demo very quickly. So what I'm showing here, I see you, Naveen, we'll address in a minute. I'm showing here traffic going from our AP to one of our state pals. You can see I've got MCS 11, 80 megahertz, so 1.2 gigabit per second physical layer, over a gigabit per second of throughput. And I've got a separate state pal, and I'm going to send traffic to that guy, and you can see it's exactly the same. This is my red guy, my green guy here. So again, very similar. I've got the same data rate, got the same throughput. But the interesting thing here is if I turn them both on, and you look at the aggregate throughput, so you know, this is the classic signature of multi-user MIMO in operation. You can see I've got only a 1200 megabit per second physical layer rate, but I'm getting over 1500 megabits per second of throughput. The only way that's possible is if I have independent physical layers, which is what multi-user MIMO is doing for me. So you can see multi-user MIMO here operating in the testbed for 11AX. Let's see. I'm going to very quickly, I know we have a couple questions to get to. The last thing I just want to show here, we're almost at the end, and then I'm going to take all your questions. The last thing I want to show here is I do want to discuss a little bit about polarization. I mentioned before that these antennas are in fact polarized, and have a little description here of how easy it is to modify the antennas in the testbed.
Change the direction that the antenna is pointing in, up, down, like that, and also left, right, like that. So again, polarization, horizontal, vertical, up, down, right.
So what's interesting about this, right, is that given the ease with which you can, you know, change the antennas in the testbed, you can actually take a look at the effect polarization would have on results. So I ran a test here where, and I'm going to show you the details of the configuration in just a minute, but as you can see, I've got my 4 streams. If you look up here, I've got 4 streams. I've got 4 RF pads. And what I'm doing in this test is one by one, I'm rotating the antennas as just shown to go from linearly polarized to cross-polarized, or you know, polarized to cross-polarized, so that and you can watch each as I turn down each one of those antennas, the received signal level drops. And let's take a look at the details behind that drop. It's a little hard to see at this scale, but this is the test I did. So if you look at the device under test, you can see that the antennas, you know, are clear, sort of dipole-like antennas. You can see their polarization. And if you look at our antennas, it's this set of 4 up here. So you can see I initially had them aligned with the device under test. And then what I was doing was individually turning each one so it would be cross-polarized like that. And if you look at that data, kind of zoom in on it, you can see the effect. It's actually a fairly significant effect. We're looking at about 15 dB from cross-polarizing the antennas. So you can see a fairly noticeable drop in the received signal level. So just quickly, let me quickly kind of summarize a little bit about antennas, everything we've discussed today. So it's important to know that antennas, right, have frequencies of
There is a
operation.
raised hand if you'd like to take a question from the.
I'm going to finish this slide and then I'm going to take all the questions because this is the last slide. The antennas, they have frequency of operation, they have gain, they have directionality. So it is important to choose the right antenna for your testing. Polarization does have an effect, and so it's best practice to align the test antennas with the dud antennas whenever possible. You need at least as many RF paths as spatial streams to do this MIMO testing. You can have more, but you can't have fewer. And if those paths are reasonably well separated and the chamber environment allows the separation of many spatial streams, as we showed, you can actually, do high order MIMO testing. And so most importantly, a well-designed small form factor RF chamber can be an excellent low-cost environment for testing high-order MIMO, beamforming, and other advanced wireless features. So with that said, I know there were a bunch of questions, so let's take them all right now. Do we have?
Good morning, Lee.
Yeah. Hi. Good morning.
Yeah. So I do have one question. So there is a feature called antenna diversity. So for choosing the right antenna, do we have this feature tested? Antenna diversity?
Yeah, I mean, antenna diversity usually refers to the fact that, let's say on the AP side, the receiver itself will be getting signals on all of the antennas, and the receiver can choose how it wants to use those antennas, right? It might choose to be able to do high order MIMO, right? Or it might choose to simply pick, the receiver with the best signal level and go with that. So, I think the point about antenna diversity is just that the antennas need to be in sort of a different enough environment that the receiver can treat them separately, and we can see that it is able to do that by the fact that we do get high order MIMO. So in fact, it's able to actually differentiate multiple spatial streams, not only use it for something like, maximal ratio combining or straight, antenna diversity.
So Lee, a little bit along those notes, there's a question here from Nihar, is asking about antenna polarization and whether it can be used as an independent path. He's asking, is antenna polarization also important for OFDMA gain, and can you get OFDMA benefits by using polarization?
Well, that's interesting. So OFDMA doesn't strictly require spatial separation in any way, right? OFDMA is doing separation in the frequency domain. We have heard that you get better OFDMA performance, for example, when the devices that are being used have similar received signal levels, and so to that, at that level, it might be important to think about making sure that your devices, have the kind of similar RF paths, but at least, I haven't seen that. I have not seen that polarization makes a big difference in OFDMA. I will admit that I haven't tested that in great detail yet, but from a theoretical point of view, OFDMA is focused more on the frequency domain than on the spatial domain.
If I may jump in, also, the question could mean another thing, like in a small device like a phone, your antennas are necessarily close, and so it's going to be hard to send two different streams because being close, they will hear the same thing. And if spatially they hear the same thing, you cannot send two streams, but what you can do is polarize them, cross-polarize them. And in fact, it's a common trick in a small device, an IoT device or a phone, to cross-polarize so that you can get multiple streams. Regarding OFDMA, of course, you get multiple streams by virtue of phasing and frequency offsetting. And so you don't need that diversity to put multiple devices on the link. But for MIMO, for MIMO you do, and it's a common trick to use polarization to get more streams.
Yep, exactly. That's true. Yep, for MIMO, that's exactly true. I know we've gone a little bit long. I'm happy to stay and take questions, but that is the end of today's tutorial. Next week, we're going to talk about test methodologies, well, not next week, next seminar, which should be in a week or two, real life versus controlled testbed. But as always, if there are topics that are of particular interest to you, feel free to send them in and we will try and work them into the series. So thanks very much for attending. As I said, I will stick around. For those of you who were not aware, all of those tutorials, including this one, are recorded and have been posted. So this is the set so far. We'll be adding this one. And you know, please, if any of them seem of interest, go back and take a look.
Yep.
Thank you folks for attending. We have another session at 4:30 Eastern and then a third one 10:30 Eastern.